Hello everyone, and welcome to our next lesson on patterns, and we're going to talk about fractals. Now, we kind of got into fractals yesterday when we were talking about Sierpinski's triangle, because that actually is an example of a fractal. Okay, and so remember yesterday we were drawing this, and we started with the big triangle, and then we made that triangle, which made 4, and then we made these ones, and then get smaller and smaller and smaller, and really you can keep going on that forever following the same pattern, and that's kind of the idea of a fractal. Okay, and this is a 3-dimensional version. I had a neighbor 3D print for me, which I think is pretty cool. It's fun to be able to actually handle it, manipulate it. Okay, so let's talk about fractals. I have a nice little storybook talking about fractals, mysterious patterns. Dun, dun, dun. All right. On a street, in a town, in a city, familiar shapes are everywhere. There's spheres and columns, all that stuff. Some are spheres, some are cones, some are cylinders. These shapes were made by people. For a very long time, people had names for only perfect shapes, shapes with straight lines, smooth curves, or flat surfaces, right? So we have a sphere, we have a cylinder, we have, flat walls or rectangles. This is outside the Louvre in Paris, and so that's actually a square-based pyramid. Okay, so in a backyard, in a field, in a forest, things that grow in nature also have shapes. Some, like these tomatoes, are similar to, but not exactly like those shapes. So, those tomatoes are pretty spherical. The cucumbers are kind of conical. No, I mean, cylindrical. There it is. Cylindrical. Tomatoes are like spheres. Cucumbers are like cylinders. Icicles are like cones. But many natural shapes do not look anything like the familiar perfect shapes that people make. Instead of being straight, smooth, and flat, many natural shapes are rough, bristly, and bumpy. Most mathematicians and scientists thought natural shapes were too messy for people to categorize or to use to think about the world. Like, what shape do you call the broccoli besides a tree? And then if you call it a tree, what shape is a tree, right? Same thing with this flower. It's very tree-like, kind of like the broccoli, but what does that even mean? Okay, or this is a fern leaf, okay? Not until 1975, guys, in the grand scheme of things, that's not a long time ago. We did not have a name for these things. Then a mathematician named Benoit Mandelbrot noticed similar patterns in these natural shapes. He agreed that the natural shapes, which he named fractals, were very different from perfect shapes and didn't look much like one another. But he saw that what they had in common. Every fractal shape has smaller parts that look like the whole shape. Fractals are everywhere in nature and can form in many different ways. A tree is a fractal. It starts with one shape, with a stem that splits into 2 branches. Then each branch splits into more branches, and the branches split into more branches. Many smaller parts of the tree, large branches with smaller branches and twigs, looks like the whole tree with its trunk and branches and smaller branches. So look at this tree, and you see how if we look at this one branch, that really could be its own tree, and so on and so forth. The head of broccoli is also fractal. When broccoli is pulled or cut apart, each smaller part looks like the whole shape. All fractals have parts that repeat at different sizes. Okay, so you got the whole broccoli, and then we got one piece of the broccoli, and then one piece of that broccoli, but that still kind of is the same shape as the original broccoli, and so on. Queen Anne's lace flower heads with a fractal pattern, but they don't form like trees. Instead of adding parts over and over again, the Queen Anne's lace produces a bud that opens over the course of days to reveal a fractal flower. So it starts there. Okay, so each one of those then opens up to here. The large flower head is made of smaller flower heads, each on its own stem. The smaller heads, too, are made of even smaller 5-petal flowers. So can you see they separated them out there. Okay, fractals have edges that are jagged, wriggly, or craggy. This lightning splits off into many smaller sized spikes in a jagged pattern. The pattern looks like branches of a tree, though lightning forms in an instant and a tree takes years. Okay, so you can see each branch of that fractal of the lightning, if we zoomed in on it, would look like all the rest of them. Okay, there are also fractal patterns on the Earth's surface. Looking at the Colorado River from outer space shows us the fractal pattern of smaller rivers and streams that feed into the larger one. With fractals, the shape can change the same way over and over again by adding on, as when a tree grows branches, twigs, and leaves, or the shape can change the same way over and over again by creating new paths, as when water runs downhill and carves new channels in soil, rocks, and sand to create a river. So you've got the main river here, but then you've got little rivers that feed into it. And so if we zoomed in on each one of these, then it would have smaller streams coming in and out. The Grand Teton mountain range formed at least 9 million years ago when pressure below the Earth's crust pushed one giant slice of rock against another so forcefully that it created towering peaks. Just like a head of broccoli is made of many smaller sized florets, the Grand Teton mountain range is made of many smaller sized mountains. Some fractals form in a flash like lightning or in a growing season like broccoli or Queen Anne's lace. Others, like trees or rivers or mountains, take hundreds or thousands of years. Okay, but you see how like craggy the mountain is? But then you could like zoom in on one of these points and then you zoom in and then that's going to be all craggy, and then you can zoom in on even one of the more points and you can just keep going and it looks the same. There are also fractals inside of living things. This leaf's veins, which move water and plant food around, make a fractal pattern. Okay, so again, you have the main veins, but then you have little veins coming off and little veins coming off of those. This picture is super cool, I think. Trying to get the light so that you can see it. There are even fractals inside our bodies. Human lungs hold fractal shapes, which can be seen in airways and veins and arteries. In the photo below, the airways are in off-white, while the veins and arteries are blue and red. The veins and arteries are not present on the left side, just to better show the airways. Lungs continue to develop inside our bodies through our childhood, growing like a tree to fill the space inside our chests. Okay, but you can see that like you have the main branch and then you can have this branch, but then that branch is coming off and then there's little branches that are coming off of that. So it very much is a fractal pattern. And this, in one of the videos I'm going to show you, they say how the surface area of the airways in the lungs is something like a football field long, but it fits into the size of our chest, which is cool. Not every pattern with similar shapes is a fractal. The sections on the outside of this pineapple form a repeating pattern, but each section is about the same size. Not a fractal. The skin markings on these swallowtail caterpillars also form a pattern, but instead of repeating at smaller sizes like broccoli or Queen Anne's lace, each stripe and dot is roughly the same size. Not a fractal. Because of what Mandelbrot discovered and what he taught us about the patterns in our complex natural world, we can make sense of things that once seemed too messy, too small, or too large to understand. Mandelbrot gave us a word, fractals, and an idea that helps us see the world in a whole new way. What the book doesn't discuss is that there is a lot of math behind what Mandelbrot did. I'm not going to make your brains hurt with it, but just know that there's actually a lot of math behind all of this stuff as well, which I think is super cool. Fractal shapes we see in rivers, trees, mountains, flowers, vegetables, and even in our own bodies tells us a story about how things grow and change over time. The fractals may not be perfect or smooth, but they display patterns and an order of their own. Everywhere and every day, nature is forming fractals. And we live with mountains like this, and so that's not even a surprise to us. Okay, and so then it takes us through making the Sierpinski triangle again, and it shows a three-dimensional one in 2 dimensions. You know, it's fine. This is a Sierpinski tetrahedron, a triangular pyramid. See, and mine is a square-based pyramid, and so that's why it's not exactly right or exactly the same as this. Anyway, 3D printers are cool. All right, so that's kind of the basic idea behind the fractals. I'm going to post a little video that talks a little bit more about it. There's several famous types of fractals. Sierpinski's triangle is one of them. The Mandelbrot set is another famous set of fractal patterns. And then the little video I'll attach talks about I think it's the Koch. Yeah. Anyway, then I want to show you just a little piece of this because it's a TED Talk by a guy who actually has met Mandelbrot and listened to him give a talk and has created a really cool fractal app. And so he kind of describes fractals again in a little bit. Anyway, I thought this was pretty cool. So I'm going to just hold this.
200 years ago, William Blake wrote this verse. To see a world in a grain of sand and a heaven in a wild flower. Hold infinity in the palm of your hand and eternity in an hour. Now, poetry is often subject to interpretation, but I think we can all agree that this poem is about fractals. And that's pretty impressive because fractals weren't discovered until 170 years later. But Blake's poem captures something essential about the natural world around us. It draws a connection between the very large and the very small, and it observes that similar patterns can occur at vastly different scales across time and space. And we see this in the universe around us, similar patterns from the shape of immense spiral galaxies, to the weather patterns of a hurricane, to little eddies in a stream. And whenever you have a single object that contains these patterns repeating over and over again at many different scales, and where every small part resembles the whole, that's a fractal. And we see them around us everywhere, from the jagged shapes of lightning bolts to the rough, ragged edges of coastlines. But fractals are not just outside of us. Our lungs are fractals. That's how they manage to pack the surface area of a tennis court. Hold it down into your rib cage.
There you go.
And our circulatory system is a fractal as well, which is how 60,000 miles of branching blood vessels and capillaries fit inside every human being. So I'm able to stand here and talk to you today because I'm a living, breathing fractal, and so are you. But for hundreds of years, these complicated geometric shapes were swept under the rug. They were considered too complicated to mathematically analyze because they don't behave like circles or squares or triangles. And the assumption was that any explanation for these shapes would have to be as complicated as the shapes themselves. Because ordinarily, simple things have simple explanations and complex things have complex explanations. But every once in a while, something comes along that breaks the mold. Take the universe. 100 years ago, there was a crisis in physics. Measurements of the natural world weren't working out the way that scientists expected. And physicists were tying themselves in knots, coming up with more and more convoluted theories, trying to explain away these discrepancies. But then this guy showed up with a very simple equation. And this led to the discovery of the theory of relativity and opened up an entire new era in physics. 70 years later, geometry was in a similar crisis because mathematicians still couldn't explain the properties of these complex shapes. But then this mathematician, Benoit Mandelbrot, found himself studying an equally simple equation. And from this simple equation, this unlocked the mysteries of these complex shapes, and it led to the development of the entire new fields of chaos theory and fractal geometry. So let's take a look at this equation. Z goes to z squared plus c. And the way that this works is that you take a small number, you square it, you add the original number, then you feed that back into the equation, square it, add the original number, and you process it over and over each time, feeding back in the original number to keep the process going. And for some numbers, not much happens. It just stays small. For other numbers, it just bounces back and forth. But for other values, it grows very quickly, and it quickly. And it's possible to compute this by hand for 10 or 100 or 1,000 different numbers, but to get a true idea of what's really going on, you need to do this with a computer for millions and millions of numbers in 2 dimensions. And when you do that and plot the results, you get this fantastic shape, the Mandelbrot set, a shape of infinite complexity generated from such an incredibly simple formula.
Okay, so I'm going to pause this here for a second. So in the Mandelbrot set, the stuff that's in white there is when there's a finite solution to that equation that he showed you. That the limit actually comes to a number. Everything that's black on the outside is when it goes to infinity, one way or another. And so what the white bits there are showing are solutions that actually have numbers to that equation that Mandelbrot came up with.
This shape changed my life. Now, my parents' first inkling that I was mathematically inclined was when I was quite small, and I announced to them that I was going to count to infinity. And so they humored me and they bought me a 70-page notebook. And I got started. And it was going along pretty well. I think I was actually getting most of the way there. And so...
To infinity, sure. Bless his heart.
And so, as you can imagine, when I discovered that I could make a computer do this sort of thing for me, and also produce images as complicated and as amazing as the Mandelbrot set, I was completely hooked. I would write a computer program, go off to summer camp for a week, and run back to find that it had almost finished drawing one picture of a fractal. This image was from a paper I wrote in the 9th grade, and it literally took the computer a week to draw. But in that paper, I had this crazy idea. I thought that if you could make enough of these pictures and put them back to back, you could make a movie of flying through the Mandelbrot set. Of course, in the 1980s, that was a crazy pipe dream on a home computer. But fortunately, computers have gotten a little faster since then. For perspective, in the Apollo era, in the 1960s, the sum total of all the computing power in the world was about 10 gigaflops, about 10 billion instructions per second. By the late 90s, IBM was able to pack all of that power into a single supercomputer the size of a refrigerator. By 2011, it could fit into your pocket. And extrapolating ahead just a few years, all that power will be able to fit into a single grain of sand. So let's do that zoom into the Mandelbrot set. And now it can be done in real time on a cell phone. And so I'll zoom in just a little bit. And by a little bit, I mean a factor of 100 million, because mathematically, there's no reason to stop there. This shape literally goes on forever. You really can hold infinity in the palm of your hand. And in addition to complexity, you can see the self-similarity that buried deep down within the Mandelbrot set are little copies of the original shape. In 2010, Mandelbrot himself gave a talk at the TED conference in Long Beach, and I was lucky enough to be there and to get to meet him. And as you can imagine, that was a real TED moment for me. And I think he would have appreciated that buried deep down within my fractal talk is a little copy of his fractal talk. And so I showed him what I was working on, this program on the cell phone to fly into the Mandelbrot set, and he was amazed. He said it was superb that such a thing could now be done on such a small device. And it felt like the passing of a torch, and I felt like I should run with that, and I wanted to run with that as far as I could. Now, the Mandelbrot set is very beautiful all by itself, but when you look at natural fractal shapes that occur in the real world, they have color and shading and lighting and texture, and I wanted to bring that into the images that I was creating. And I found that if I took the space surrounding the Mandelbrot set and distorted it, using techniques similar to that used for paper marbling, not only it would give it much more visual richness and complexity, but it also reveals more of what's happening mathematically in the area outside the shape. Just as when you put smoke into a wind tunnel, it reveals patterns in the airflow that would otherwise be invisible. And so using this technique, here are just a few of the textures and patterns that we've uncovered hidden in the math. Occasionally, someone will tell me that these images belong in a museum. But I think that's a terrible idea, because at the museum, the first thing they tell you is, don't touch the art. But we're all walking around now with touchscreen supercomputers in our pockets. Fractals should be all about touching the art. It should be an interactive, immersive experience. And so that's what I set out to create, working with the legendary graphic and user interface designer Kai Kraus and another Fractal expert, Tom Bedard. This is the app that we came up with. And you might notice that something is missing. There are no numbers or equations or scary math. And that's very intentional, because we do want to get people excited and interested about math. And we think that the best way to do that is not to shove a bunch of math in their faces, but to show them something inspiring that can be done with math and let them discover the inspiration all for themselves. And so this is the app in action. And when
So I'm gonna stop it there. I don't know if I found the exact app that he made, but I did find a cool factory or fractal app. And this particular one is called the Phoenix. And you can go in and change the color set that you want to. We'll do B. Oh, sorry, there's an ad. All right, so you can change the color, you can change how it fills in the background, and then you can zoom. And you can zoom and zoom and then zoom and keep zooming in. And then it's just gonna keep going and going and going and going, okay? So this is actually a pretty cool app. There's several Fractal apps out there. But anyway, they say that this is really good for helping to calm your mind when your mind is having issues and stuff. If you're stressing out, playing around with a Fractal app like this can maybe help calm your brain down a little bit. So we can change, let's see what happens if we go lights. See, and it's going to start changing the background of it a bit. Whoop. Anyway, so fun stuff. Fractals are cool, and it's math, and it's awesome.